Hey guys, Mr. Klein here with our next lesson in our chapter on atoms in the periodic table. This will be a 2-lesson chapter, so let's go ahead and let's get going. Now, this lesson we're going to be talking about the history of the atom. So in many ways, this is like a history lesson with a little bit of science review of parts of the atom thrown on top of it. And as you know, throughout science, new knowledge comes with new experiments, and we check what knowledge is currently, and we use experiments to see if it's true, or if we have an idea about something, we'll use experiments to find the data out in order to see if the theory needs revising or being fixed. And the thing about the atomic theory, or the theory of what the atom looks like, it's difficult because atoms are so small. Because we can't really see them. We can only really kind of see them in a slight way with a very, 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 very powerful electron microscope. And so we can't exactly see them directly. So a lot of this stuff has come from indirect observations. In other words, what we see when doing things without looking at it directly. Now, if we go back about 2,500 years, to around 430 BC, a Greek philosopher named Democritus proposed that matter was formed of small pieces that couldn't be cut into smaller parts. And he called those atomos, which is where we get the term atom. And an atom is the smallest particle that can still be considered an element, or the one that we use in our class normally is that the atom is the smallest unit of matter. Anything smaller than that is considered a subatomic particle. And like I just said, the atomic theory grew to its modern form as a series of models that developed from experimental evidence. So we would see something in an experiment, it looked different than we were expecting. We did more experiments that confirmed it, and it changed the atomic model. As more evidence was collected, the theory and the models were, of course, revised. And the main reason why we get more evidence is technology advanced. In other words, scientists were able to develop new methods of observing indirectly the atom, which allowed us to gain more understanding about it. So let's start with English chemist John Dalton. And John Dalton thought that atoms were like smooth, hard balls that could not be broken into smaller pieces. And here's John Dalton. He's an English chemist, in many ways considered one of the fathers of chemistry. And he created the first atomic theory that stated the following. Now, some of this stuff, of course, as we'll find out, got completely overwritten over time, but some parts of it actually we still believe today because it's been confirmed through evidence. First off is that all elements consist of atoms that cannot be divided. That, of course, is not true anymore. We know that we can split them into subatomic parts, such as protons, neutrons, electrons, quarks, things like that. Now, all atoms of the same element are exactly alike and have the same mass. And atoms of different elements have different masses. This point of John Dalton's atomic theory is still considered true. To an extent, isotopes, which we'll talk about later on, have different masses for the same atom, but atoms of different elements do have different masses. Now, an atom of one element cannot be changed into an atom of a different element through a chemical reaction. And in a way that's still true. We can smash atoms and we can break them down and stuff like that. But for the most part, for most normal circumstances, we can't change one atom into another through chemical means. We have to like physically break them apart. Now, compounds are formed when atoms of more than one element combine in specific arrangements. This is true. This is still true, that compounds are formed when two or more atoms combine together chemically. That's our definition for it. Now, this right here is John Dalton's model of the atom. As you can see, it's one big piece and you can't break it down. So that's John Dalton's atomic theory. So we fast forward and we go all the way to 1897. John Dalton's was about 200 years previously in the 1600s. But Thompson in 1897 observed that atoms contain negatively charged particles called electrons. Electrons, of course, have a negative charge. And because scientists knew that atoms themselves had no electric charge, Thompson reasoned that atoms must contain some sort of positive charge, meaning that the two charges canceled themselves out. Because if he was able in his experiment to figure out that there was a negative charge and it gained no overall charge, there had to be something positive. That was an inference he made. And this right here is J.J. Thompson. He, of course, is an English chemist also. And J.J. Thompson changed John Dalton's model of the atom, and it looks a lot like a watermelon. And according to J.J. Thompson and his atomic model, this is what it looked like. He figured that there were these little negative bits called electrons floating around, but the rest of the atom was completely positive. And so we've gone from Dalton's model of a single unbreakable piece to J.J. Thompson's model including electrons. We're starting to get more toward the modern idea. Now, one of J.J. Thompson's students was Ernest Rutherford. He was a scientist, and he found evidence that challenged Thompson's model. And here's what happened. He did a very famous experiment, and he shot positively charged particles through some gold foil. Now, according to Thompson's model, the particles should have passed straight through the foil or bent slightly because of the positive charge that was spread out through the gold atoms. Because if you remember, Thompson's model shows that all of this was the positive charge. So it should be either bent slightly or they would just pass right through. But when he did the experiment, few particles were bounced off at large angles. It was almost like they hit something like a pool ball and flew off. Based on the results of the experiment, the model stated that the atom is mostly empty space because they kind of flew through pretty much straight ahead, but it has a positive charge at its center. And Rutherford made an inference that the center of the atom, which he called the nucleus, yes, that's what we call the modern center of the atom, the nucleus, the positive charge was held closely together. And this is the model that he gave. So we have all this empty space, the electrons float around, and here in the nucleus we have the positive charges. And a good example of Rutherford's model is to look at the inside of the cherry, where you have the little cherry seed. That would be the nucleus. The rest of it would be the electrons are at. And of course, the positively charged particles in the nucleus were called the protons. So those are the So as you can see, we have protons and we have electrons and we have a nucleus. Now we're getting toward our modern understanding of the atom. And a Danish scientist named Niels Bohr decided to take things a step further. He was a student of Ernest Rutherford. And here's a picture of Niels Bohr. Bohr was from Denmark in Europe. He modified the Rutherford model to include a discovery that electrons are only found in specific orbits, much like the planets orbit the sun in the solar system. And here's a more advanced model of Bohr's atom, talking about the wavelengths and stuff like that, and the changes of energy based on the electrons. But essentially, much like if this would be the sun right here, and the planets orbit around the sun, Niels Bohr said that the electrons would orbit the nucleus much like that. Now, in the 1920s, it's only a few years after that, scientists determined that unlike Bohr's model, they figured out electrons actually don't orbit them just like planets. Instead, the model stated that the electrons move around they don't move around like the planets. Now, the electrons move in the cloud is related to its energy levels, or the specific amount of energy that the electron has. And this theory, this cloud model, was developed by a German chemist by the name of Erwin Schrödinger. And Erwin Schrödinger is, of course, famous for Schrödinger's cat experiment. And Schrödinger said that the energy levels were pretty much the same thing as the orbits, that electrons would float around in those specific energy levels rather than this. But for in Bohr's model, but for simplified models of the atom, we do use Bohr's model right here. And so here's a generated image of orbital clouds of a hydrogen atom. And as you can see, this big white area is the highest energy, where negatively charged energy, and that's where the electrons go out. And this goes in all the way to the nucleus at the center. So that trip through history, I'm pretty sure you're kind of asleep, so you need to wake up. And so let's go ahead and let's talk about our modern model of the atom. In 1932, so less than 100 years ago, we figured out that there was a particle in the nucleus with no charge called a neutron. And the neutron was kind of what allowed the protons to stick together. And so let's talk about the modern model of the atom, which looks a bit like this. Okay, so you have your cloud of electrons, they float around right here, and in two atoms, that's the average distance, whether it's their ground state or their excited state, if energy is added. But in all of these dotted areas are kind of where the electrons would probably be at. And we don't quite know because of the Heisenberg uncertainty principle, among other theories with that. Now, the modern model of the atom, the nucleus is tiny, dense, and contains protons and neutrons. And surrounding the nucleus is a cloud-like region of moving electrons. And actually, most of the volume in the atom is actually empty space. If you think about it this way, if you think about an atom as like a football stadium, you could have in the nucleus at the 50-yard line in the exact middle of the football field or at the center line of a football pitch, for those of you who watch soccer, you could have the nucleus. Let's say it'd be like a baseball or cricket ball. It's sitting there in the middle. And the electrons would orbit on that scale and the outside, almost at the outside of the stadium, like in the really cheap seats. So that's how much of what we are in reality as is actually empty space. Kind of crazy. Now, so that's the model of the atom. So we have the protons and neutrons in the center, in the nucleus. The electrons orbit them, and we don't quite know where they're at exactly unless we're directly observing them, but we can kind of figure out where they are based on the energy levels, and those are shells where they're in. So in atomic models, protons have a sign as a plus, and electrons are represented by the symbol E minus, where the E stands for the number of electrons. So you would have like a 5 minus for that. So in order to determine the charge, use the scale of +1 for each proton and -1 for each electron. If the numbers cancel each other out, then the charges cancel, making the atom balanced. And if they don't balance, if it has a positive or negative, it's called an ion, which we'll talk about later. And neutrons, of course, don't affect the charge of an atom because they have a charge of 0. Because the neutral, they're an N for neutral. So remember, protons have positive signs, electrons have negative signs, neutrons have no charge. And so we're just going to roll through some last stuff right here real quick. Now, it takes almost 1,840 electrons to equal the mass of a single proton. Electrons are really, really lightweight. They have almost no mass at all. But a proton and a neutron have about the same mass, and so we compare the masses of particles and actually atoms themselves. We don't use metric units, rather we call a unit called atomic mass units, or AMUs, which is about equivalent to the mass of a proton or a neutron, since they do have about the same mass. So if something has 15 AMUs, it has the mass of about 15 protons or 15 neutrons. Speaking of protons, the big thing, we'll talk about different types of atoms with different extra or not enough electrons. Later on in a second, we'll talk about atoms with extra neutrons. But you can't have the same atom with extra or fewer numbers of protons, because that is the key thing. Every atom of the same element has the same number of protons. And this number is what we call the atomic number. That is the number of protons in the nucleus of an atom. So if you have 6 protons, it's always going to be the same type of atom, no matter the number of neutrons or electrons in it, because if you add a proton, it becomes a different element. Now, what happens if we add neutrons? Well, I'm glad you asked as we go and we finish off this really long lesson. Even though all atoms of an element have the same number of protons, like I said, the number of neutrons can vary because you need the neutrons for the protons to stick together. Now, atoms with the same number of protons but different numbers of neutrons, we call them isotopes. Okay, we call them isotopes. And an isotope is identified by its mass number, which is the sum of the number of protons and neutrons in an atom. And this is really easy to figure out. For example, the most common isotope of carbon is carbon-12, which means that there are 6 protons and 6 neutrons. Because you add the 6 protons and 6 neutrons, it gives you 12. Okay, so that's a total mass in there. Now, an isotope of carbon is carbon-14. Now, we know it's going to have 6 protons because it's carbon. If it has more than 6 or fewer than 6, it's not carbon. So all you do is you take the number 14, you subtract 6, and yes, that's how many neutrons you have. You have 8 of them. So to sum up this section right here, if you have extra neutrons, it's an isotope, and we identify isotopes based on their mass number, which is the total number of protons and neutrons. remember, all you have to do to figure out the number of neutrons an isotope has is you subtract that total, which is this number on the dash right here, by the number of protons you know the element has, and you get the number of neutrons. So, 15 minutes, I know. Really long lesson, but we went through the entire atomic theory and we went over the basics of atoms as a nice quick review. Now, in the next lesson, we'll be talking about the periodic table. So, as always, if you have any questions, please let me know, and thanks for watching.